Double-slit diffraction. In 1801, Thomas Young put together an experiment to see if light behaved like water waves, forming ripples after it passed through two openings, the double-slit experiment. In the case of water waves, the interference effect becomes more pronounced as the wavelength of the water wave approaches the width of the opening. Since the wavelength of light is much less than that of water waves, the openings would have to be very small to see any effect. But first, let's assume that light acts like a particle and predict what would happen if a beam of light particles strikes a wall with two holes in it. Let's use the analogy of thrown baseballs. Imagine a baseball player throws a large number of baseballs through openings in a wall a little bigger than the size of the ball. The top baseballs would all hit the red target, and the bottom ones would hit the blue target. There would be two piles of baseballs. If light was just a large number of particles, one could expect a similar pattern on the back wall, two bright spots. Young conducted his experiment passing a single color of light through two slits. However, he did not see two bright spots on the viewing screen. He saw a pattern looking like this here, consisting of alternating bright and dark lines, or also known as fringes, which decreased in intensity from a peak in the middle. Here's Young's sketch of the results, with points A and B representing the sources of the monochromatic light, and with C, D, E, and F as minima, and the areas between them as maxima. So minima are the points where there's destructive interference, and maxima is where there's constructive interference. On the right is a photo of the light pattern on the screen after passing through two slits. It's the same pattern that results with sound or water waves. Thomas Young concluded that light, like sound and water, travels as a wave. Interference occurs because each point on the screen is not the same distance from both slits. Depending on the path length difference, the wave can interfere constructively or destructively. Right in the middle is where you're going to get the brightest spot, and that's because both of these waves are going to travel exactly the same distance to get to that location. However, at other locations on the screen, like here, this wave only had to travel that far, whereas this wave from the top slit had to travel farther. Waves will constructively interfere at a point when they're in phase, when their crests coincide. This occurs when the distance the two waves travel differs by an integer number of wavelengths, like one full wavelength or two full wavelengths. For example, if you have one light source here and one here, then all of these waves are going to travel the same distance. But if you have one source here and then one source here, maybe this wave, this is one wavelength, and then they meet up here, those will still constructively interfere because they're one wavelength apart. This will result in a bright fringe. Dark fringes occur where the waves destructively interfere, when the waves are 180 degrees out of phase, which is when crests line up with troughs. This is like having another source here, like half a wavelength, lambda over 2 away. So that will create, because you have your wave going this way, you have your wave here, these are now out of sync. One wave is here, the middle, the crest lines up with a trough. These occur between the bright fringes. In this case, the waves cancel out and the amplitude is 0. We'll see this in more detail on the next slide. All right, here's our double slit setup. We have our light source, we have our two slits, we have our viewing screen. Now there is a bright spot at this location. Let's figure out why. The light traveling from the top slit to that location travels exactly this far, this distance here. However, the light from the bottom slit travels farther. How much farther? Exactly that amount farther. So if that is one wavelength, or two wavelengths, or any integer multiple of the wavelength, they will still be in phase when they get to that location, after which they will travel exactly the same distance. So their crests will still line up. So here you can see this wave is traveling 2 wavelengths farther, but the crests still line up, the troughs still line up, they are still in phase. Using the same example as before, we had a bright spot up here, but now here we have a dark spot. There's a dark spot here because the bottom wave has traveled either 1.5 wavelengths or 2.5 wavelengths, etc., farther than the top wave. So this extra distance here is no longer an integer multiple of a wavelength. It is now some integer plus 1/2. So this means the waves are not going to be in phase anymore. Here is a little close-up where this bottom wave has traveled 2.5 wavelengths farther than the top wave. So now this crest is lined up with a trough and we get destructive interference. They are now out of phase by the time they reach this point here. And then they travel the same distance after that, but now they're out of phase. Since this path length difference between the upper ray and the bottom ray is crucial in determining where bright and dark spots are going to be on the screen, let's calculate the path length difference. We're going to name it S. Since L, which is this distance, is much, much greater than the distance between the slits, and we're also going to assume that this angle here is really small. Like to scale, the slits are like over here, the screen's like all the way over here. So if you draw it like this, we can assume that this angle theta is really small. We're going to assume that these two rays leaving the two slits are essentially parallel when they leave. Now we do have this red dash dot line here indicating there is a break, and this is just because we can't draw it to scale. So here where the rays are leaving the slits, they're essentially parallel, and then eventually the rays do converge at point P, but there's a lot of space between this part and this part, which is why we're doing these little red lines as a break. All right, so the first thing we're going to do is drop this line from the top ray to the bottom ray that's perpendicular to the bottom ray. That's going to give us a right triangle where the hypotenuse is D, the distance between the slits. S, which is what we're looking for, is over here, opposite this angle theta, and Y will be adjacent to that angle. And sine theta, remember SOHCAHTOA, sine is opposite over hypotenuse. So therefore, sine theta is S over D. All right, so next we're going to draw this dashed line here, right from the middle of D over to the observation screen and then up to point P. So we have a right triangle here. What we are going to now show is that this angle theta is equal to this angle theta. It's time for a little geometry. All right, so now if we draw a red dashed line here that's parallel to this orange line, we have a right angle right here, which means if this is theta, that means this angle is the complement. It's 90 minus theta, right? This angle plus that angle must equal 90. Now look at this ray. We have this ray is parallel to that ray, and we have this line that's right angle there, which means this is also a right angle between there and there. So remember, if this is 90 minus theta and this is a right angle, that means that this angle must also be equal to theta, right? This angle here plus that one is 90, just like this angle plus that angle is 90. All right, so since this angle is theta, that means this angle is theta, because this line is parallel to that line, this ray is parallel to that ray, so those angles are equal. So the path length difference between the two rays is d sine theta. Remember, sine theta, so that's theta right there. Sine theta is S over D, so therefore S equals d sine theta. That is the path difference between the top ray and the bottom ray. In this expression, d sine theta is going to work for all angles. All right, in a few slides, we're going to be figuring out this distance here, x. But it's good to know that you will get a bright spot on the screen when the extra distance traveled, which is d sine theta, is equal to m lambda. This will give you a bright spot when you have a double slit experiment. This equation is on the AP Physics 2 equation sheet. And just like the constructive interference pattern, the bright spot is given by this equation, we can find dark spots by changing that m to m plus 1/2. If the extra distance traveled, d sine theta, is equal to 1.5 wavelengths or 2.5 wavelengths, that's where you get a dark spot. And remember, m is going to be the order of the interference fringe. So the first bright spot will have an m value of 1. The second bright spot will have an m value of 2, and so on. Many times it's easier to measure this distance x instead of theta, since you can measure this with a ruler, right? If you did this experiment and you had an observation screen, you could just put a ruler and measure the distance to the first maximum, whereas measuring the angle would be much harder. Also, because this angle is small, we can use small angle approximation. So what that means is that if an angle is less than 15 degrees or approximately 0.26 radians, the tan theta is going to be equal to sine theta, which will be approximately equal to theta. Because the triangles are similar, let's look at this here. So sine theta is going to be opposite over hypotenuse, s over d. So because sine theta is approximately equal to theta, since it's a small angle, theta is approximately equal to s over d. Now here, tan of this theta would be opposite over adjacent. That's x over L. So tan theta is approximately equal to x over L, but as we went over here, tan theta is approximately equal to theta. So we have s over d is approximately equal to x over L, and that's what we have right here. Now we can multiply d to the other side, and then previously we figured out that s, this distance here, is equal to m lambda. Remember, we had d sine theta equals m lambda, but d times sine theta, well, what is sine theta? S over d. So we have s over d, the d's cancel. So s is equal to m lambda, so we put that in there. Solve this equation for x, and we have the location of our bright spot. We now have our equations to find maxima and minima. So for all angles, this is our equation that's going to give us the location of a bright spot in the double slit experiment. And for angles less than 15 degrees, which, as long as theta is small here, this will be true. This equation here is not on the AP Physics 2 equation sheet. You are going to need to be able to derive it from this equation here. So knowing that we can set this L and x, knowing that we can replace sine theta with x over L, so that we have dx over L equals m lambda, and then solve for x, so m lambda L over d, you're going to have to be able to do that yourself. Remember, d is the distance between the slits, x is the distance from the middle of the screen, so this line right between the two slits, up to our bright spot. M is an integer, which is, if m is 1, it's the first bright spot. If m is 2, it's the second bright spot, and so on. And capital L is the distance to the screen. Therefore, you can solve the equation here for x, which is the distance to a specific fringe. M is the number of the fringe that you're interested in. And remember, you're going to use this version of the equation for bright spots, this version for dark spots, right? If you have m plus 1/2, that's where you're going to get the destructive interference. The bright and dark spots get further apart when the distance between the slits gets smaller. So if this distance gets smaller, the distance to the fringes increases, right? Those are inversely proportional. If the wavelength of the light gets longer, then the distance to the first fringe, the distance between the fringes will also increase. And if you move the viewing screen farther away, the distance between the fringes will also increase. In Young's experiment, the intensity of the light, the brightness, decreased the farther away the bright spots moved from the central axis as x increases. But as the width of each slit becomes negligible compared to the wavelength of the incident light, the brightness does not change. This will be explained with single-slit diffraction. The width of each slit is negligible compared to the wavelength of the incident line in this plot of light intensity versus x. The peaks and troughs are identified with their fringe number m. So here's the center. We have constructive interference creating these peaks, and we have destructive interference causing these dark bands. Since the position of the maxima, except for the central one, depends on wavelength, if white light is used in the experiment, the fringes will contain a spectrum of colors. This is because light of different wavelengths will diffract different amounts. Red light will end up farther away from the midpoint than blue light. The double-slit experiment relies on two properties of waves, diffraction and interference, which enabled Young to claim that light is a wave. Each slit generates a new wave due to diffraction. Those waves then either constructively or destructively interfere on a screen, which is at a distance much greater than the distance between the slits. A diffraction grating consists of a large number of equally spaced narrow slits and is created by etching thousands of thin lines onto a glass slide. They produce maxima and minima, just like in the double-slit experiment, but the pattern is much sharper because there are thousands of slits, not just two. The more lines or slits there are, the narrower the peaks. So you can see the difference here between a regular double-slit experiment and diffraction grating, where the peaks are much taller, narrower. Shining white light on the grating produces a spectra of all the colors. Since the location of maxima depends on wavelength, the colors in white light separate out, just like dispersion. The equation for the maxima is the same as for the double-slit experiment, where d is the distance between the etchings on the diffraction grating. Diffraction gratings are labeled with lines per distance. For example, the three diffraction gratings to the left have 100 lines per millimeter, 300 lines per millimeter, and 600 lines per millimeter. To solve a problem with a diffraction grating, we need to convert lines per millimeter into d, which is the distance between the lines. So for the 600 lines per millimeter grating, here's how we would convert it. We don't want lines per millimeter, we want the number of millimeters between the lines. So we're just going to flip this over. We have 1 over 600 millimeters per line. Then we want to convert millimeters into meters. So we'll use the conversion factor. So we see it's 1 over 600 times 1,000. That's a huge denominator. That's how little space there is between the lines. 1.67 times 10 to the negative 6 meters. That's the spacing between the lines, and that's what you're going to use as d in the equation d sine theta equals m lambda.